Unit 15, pages 146 to 153. Let's make the distinction between a homogeneous equilibria versus a heterogeneous equilibria. If it's homogeneous, then all of the phases would be the same. When it's heterogeneous, then it involves reactants and products in different phases, such as solid, liquid, gas, and or aqueous. The concentrations of pure solids and liquids are equal to 1. So the solid material A as a solid is equal to 1, and the pure liquid, not a mixture, not aqueous, has a concentration equal to 1. This reaction is a heterogeneous reaction because the materials exist in more than one phase. So we have a solid, we have a liquid reactant, and we have a gas as a product. However, the equilibrium constant expression would be written as Kc is equal to the concentration of C gas raised to the power of 1 over the reactants A squared and B to the 1, except both of these values would be equal to 1. Therefore, the equilibrium expression would just be the Kc is equal to the concentration of C raised to the first power. So, in the future, you can literally cross out solids and liquids and don't include them in your equilibrium expression. So example 15.49, write the equilibrium constant expression Kc for this reaction. And we have calcium carbonate solid yields calcium oxide solid plus CO2. So Kc equals, and I'll look at my products and I'll ignore this because it's a solid. I'll include carbon dioxide because it's a gas, and raised to the first power because that's its coefficient. And then I'm going to put this over the reactants. However, because that's a solid, I will not include it either, and therefore my equilibrium expression is just Kc is equal to the concentration of CO2. Example 15.50, write the equilibrium constant expression for Kc for the reaction as follows. So Kc equals, start with our products. We will include aqueous and we will include the gas. So we'll write the concentration of NaOH squared times the concentration of hydrogen, and that's raised to the first power. And then I'm going to put this over, and this reactant is a solid, which equals 1, and this reactant is a liquid, which equals 1. Therefore, my final answer is just Kc is equal to the concentration of sodium hydroxide squared times the concentration of hydrogen. Now we're going to move on to a concept that's called the reaction quotient. When a reaction mixture is not at equilibrium, the reaction quotient, or Q, can be used to indicate which direction the reaction will go spontaneously. The equilibrium constant is defined above in equation 15.4. The reaction quotient Q is defined in exactly the same way as K. However, for Q, the concentrations are not necessarily equilibrium concentrations. So what this means is, let's take this general reaction as an example. And if I wrote the equilibrium expression, K equals P raised to the P times S raised to the S over A raised to the A times B raised to the B, I would get this. This is assuming that P, A, S, and B are in equilibrium or at equilibrium, and so these are the equilibrium concentrations. But what if the system is not at equilibrium? Well, then these concentrations are going to represent Q, the not at equilibrium reaction quotient. All systems want to be in equilibrium. However, if they're not in equilibrium, they're going to shift in such a way to get to equilibrium. And so if we have a system that is a Q value not equal to K, then we can use the Q compared to what we know the K is to figure out, well, which way is this reaction going to go? Is it going to proceed to products to get to equilibrium, or is it going to go in reverse toward reactants to get to equilibrium? So for K, the concentrations must be equilibrium concentrations. But for Q, the concentrations can be for any reaction mixture. So you can calculate Q, and maybe the system is at equilibrium, or maybe it's not, and then it's going to shift depending on Q compared to K. So, predicting the direction of spontaneous reaction based on a comparison of Q to K. If Q is greater than K, the reaction is going to move towards the reactants. So, spontaneously move in reverse. If Q is equal to K, then the reaction is at equilibrium, and if Q is less than K, the reaction will go towards products. The direction of spontaneous reaction can be determined by comparing Q to K. So here's the way I think of this. Here's my reactants, and they're going to go to products. And if I were at equilibrium, I'm going to put my K over the arrows. And so that's what I like to think of it. We're trying to be at equilibrium. All reactions are trying to be at equilibrium. If I have a Q that's less than K, so less is over here, more is over here. If my Q is less than K, then that means we want to move from Q toward K. Want to get to equilibrium. And so if Q is less than K, then this is going to move towards products because the products are this way. So it's going to move in the forward direction. Remember that if it moves in the forward direction spontaneously, then you have a delta G that's less than 0 or negative. And you have a delta S total that's going to be greater than 0 or positive anytime you have a reaction moving in the forward direction. If you have a reaction A goes to B, here's K at equilibrium, and if the Q is greater than K, so here Q is greater than K, so there's more Q than there is K, this is less, this is more, then we want to get to equilibrium. So the Q is going to move toward equilibrium, and so this means we're going to move in reverse. It's going to spontaneously move towards reactants. And so in this case, delta G is a positive value, and the delta S total is a negative value. So this is for any reaction spontaneously moving in reverse. If the Q is equal to K, so A yields B, and here is K, and Q is also here, then if Q is equal to K, then we know that it is at equilibrium already. Q equals K. Means we're already at equilibrium. This means the delta G is equal to 0 and the delta S total is equal to 0. And so there are your three scenarios. So example 15.51, determine if this reaction mixture is at equilibrium. If not, then which way is the reaction going to go spontaneously? So here's our reaction, and Q is equal to carbon monoxide gas times chlorine gas divided by COCl2. And all of these are raised to the first power. These are all gases, so they are all included in my equilibrium expression. This is the same thing as if I were to put K here, then that just means that all of these concentrations are at equilibrium. But since I don't know, that's why I'm just putting a Q here instead of K. So I'm going to insert my concentrations into the equation, and this gives us 1.42 times 10 to the 5. So 1.42 times 10 to the -5. Remember, this is going to have no unit. So now I'm going to compare this to my K. So I'll kind of make my little generic reaction here, and K is 2.19 times 10 to the -10. That's my K. And what I have for Q is 1.42 times 10 to the -5. This value is greater than K, 1.42 times 10 to the -5. And that is my Q. And that value is greater than K. So because it's greater than K, then the reaction is going to spontaneously move in reverse. And so we have a delta G that is greater than 0, and a delta S total that is less than 0, and we are moving towards the reactants. So here's a way you can think of what Q indicates. Here's your reaction mixture, and it always is reactants moving to products. And the goal is always to move toward equilibrium. So if your Q and K are equal to each other, then there is no net reaction because it's already at equilibrium. If your Q is less than K, and remember Q is equal to products over reactants, then I need the Q to become a larger value. And so that means the numerator needs to become larger. So my products need to increase. So this reaction has to move to make more products in order for Q to become equal to K. Over here, if my Q is greater than K, then that means I need the denominator to become larger so that my Q will get smaller. And so R is going to have to increase, and then this way it will allow my Q to become smaller and thus become equal to K again. Q equals K, the reaction is at equilibrium. Q less than K, as the reaction mixture moves towards equilibrium, Q must increase. For this to occur, products must increase and reactants must decrease. If Q is greater than K, as the reaction mixture moves towards equilibrium, Q must decrease. For this to occur, products must decrease and reactants must increase. Equilibrium calculations are based on two basic ideas. When reaction occurs, the changes in the amounts of each material are linked by stoichiometry. If we know that 0.2 moles of ammonia are produced, we can calculate the change for hydrogen. So if I take 0.2 moles of ammonia, divide by 2 moles of ammonia multiplied times 3 moles of ammonia, and I know how much of the hydrogen is going to be used to make that much ammonia. Therefore, I know that as this increases by 0.2 moles, this is going to decrease by 0.3 moles, and this will decrease by 0.1 mole, doing a similar calculation. When the reaction produces products, the change for products is positive, and reactants, the change is negative, meaning we're going to increase the amount of products while we decrease the amount of reactants. Number 2, the amounts of materials in the equilibrium mixture are related by the law of mass action, this equation right here. So example 15.52, a mixture of 0.50 molar nitrogen and 0.027 molar ammonia exists in a closed container at equilibrium. The fact that it is at equilibrium is a key statement. Calculate the concentration of hydrogen at equilibrium. So the good news is we're dealing in, this entire problem is dealing with at equilibrium, and we know the equilibrium constant here. So first I'll write my law of mass action. K is equal to my products, ammonia, and this will be raised to the second power, over my reactants, nitrogen times hydrogen cubed. Notice they're all gases, so they're all included in the law of mass action. So now I want to know what is hydrogen at equilibrium, and so I can plug in my value for K, 0.105 equals ammonia is 0.027 squared all over nitrogen, which is 0.50, times hydrogen cubed is what I don't know. I'll multiply this to both sides of the equation, and I'll get hydrogen cubed times 0.50 times 0.105 equals 0.027 squared. Divide both sides by 0.50 and 0.105. And this, I'm going to take the cube root of both sides of this equation in order to have just hydrogen. So hydrogen's concentration will be equal to 0.240 molar when you type this into your calculator. So here's a note card. You can pause the video and jot it down. Heterogeneous equilibria includes all phases. We want to exclude solids and liquids from equilibrium expressions or laws of mass action. Always include gases and aqueous solutions in equilibrium expressions. K is a system at equilibrium, and Q is a system out of equilibrium, maybe, because it could be in equilibrium, but we won't know unless we calculate and compare Q to K. The goal is to get to K. A system always wants to be in equilibrium. There are 3 scenarios. When Q is equal to K, it's at equilibrium. If Q is less than K, it will shift to products. If Q is greater than K, it'll shift to reactants. The law of mass action at equilibrium is these raised to their stoichiometric coefficients. products over reactants always. If it's not at equilibrium, then it's the same law of mass action, but it's going to be equal to Q, meaning we're not sure if it's equal to K or not. We want to find out.